Swayam Prabha. Digital India. Educated India.
So, in today's 2 hours lectures, I'm planning to cover two different topics. First topic is on how do you compute some of the properties of the anode materials. Specifically, these are like 2D materials. You have the vision of like a 3D material versus a 2D material, etc. So, what we are dealing everything is on a computer. Okay, that's the main point that you should remember. So these are not any experiments that we are doing inside a lab, but all the experiments are done inside a computer. And what we will be seeing here, as the heading suggests, is about computing a few properties of the anode materials of for any particular battery type. For example, you might have heard, like I remember that Anju came here and taught you something about the electrochemistry fundamentals. Okay, I'm not like that kind of person. I do not know much about that kind of fundamentals. Okay, don't expect me to write the Nernst equation or something. What I'm trying to show you here is something different, like how do you use the electronic structure theory to compute the properties. Okay, that's the aim. If we are able to finish this, then I will also try to show you something about perfluoroalkyl substances. So these are what are known as the water pollutants. Okay, how do we degrade? Again, not experiments, but inside the computer we will see, if you using the first principles calculations, how can you degrade these materials is what we would be seeing. Okay, that's the major thing. So we are going to see computing a few electrochemical properties that can help us to identify whether a 2D material can be promising anode material or not. So these are the three people who shaped my career here. So he is my PhD advisor, Professor Swayam Prabha from JNCSR. So with Professor Swayam Prabha, I have worked on various 2D materials, and I have studied their optical, electronic and magnetic properties, such as 2D materials like graphene nanoribbons and so on and so forth. I mean other 2D materials and 1D materials, etc. After then I moved to the Rochester. At Rochester, I worked with Frank. His normal name is Peng-Fei Huo. So with him, I have developed a few non-adiabatic dynamics techniques. Okay, so these kind of techniques are generally useful in order to study computationally how do you calculate the charge transfer mechanism in organic photovoltaics. So you do know that, like when you use this solar cells, you are using the sunlight. That means photons are absorbed by this material, and then you are using it to do some purposes, right? Like you are generating the voltage and using the voltage. Such kind of things when you see. So the charge transfer mechanism between the donor and the acceptor is what we have studied using these non-adiabatic techniques. After that, I moved to California, Riverside. So where I have worked with Professor Brian Wong. With him, I have worked on various kinds of things, specifically using ab initio molecular dynamics to study environmentally important reactions, as well as energy related materials and catalysis and so on and so forth. So as such, these three people are the ones who are main for my academic career. So moving on, the first question, like let's go into the talk here. So the first question is, why are we studying energy storage devices? Any answers from your side? Every application we make, we need energy. Any other things?
We're looking for renewable ways of using energy, so we need to look out for all the options available and look out for the best possible application.
Very nice. So at least some of you already know the answers that I'm going to tell, which is a good thing. So we have seen this particular picture in headlines for a long time. So why this is happening and how it is affecting us, this is one thing that you should be thinking. So whether Russia and Ukraine are fighting between each other, or America is fighting with Russia, it doesn't matter for us. Like it is going to affect the oil prices that we are going to use here, right? So why that is the case? Because we all, I mean India or many other countries, are majorly dependent on the non-renewable energy resources, such as the petrol and the diesel and other normal, even LPG gas that we are using. All this is coming from the non-renewable energy resources, and if anything happens anywhere in the world, that will have a direct effect on all of us. Okay, Obviously, none of us wanted to have that, right? Like, although our finance ministers and others are like playing a nice role so that we are not actually seeing the effect at this moment. But think of some other places, like if you consider Europe or somewhere, they had earlier at least like a serious problem with the gas supply. Gas means like this petrol and other things. And this is like a winter, harsh winter, and they cannot have the enough heating, like we are having an AC right now in this room. Similarly, they must have the heating procedure, and that is not possible for them. So this automatically suggests you that we need to go back to the renewable energy resources, but we should not be heavily dependent on the non-renewable energy resources. And it's not that today only because of the Russia-Ukraine war we have realized this. People have been knowing about this for a long time, and indeed majority of you might already know about this. And there are various sectors, as you could see here, hydropower, wind, solar and other renewable energy resources have been consistently increasing. That means we are all started to use more of the renewable energy resources, but this demand will be rising and we need to improve it further. This is definitely necessary. But what is the problem with the renewable energy resources? They produce the energy intermittently. That means they cannot produce the energy continuously, and they have, as he pointed out earlier, we cannot just simply use the energy as such when they are giving us, right? So when you are using, for example, the electricity here, we are like very sound and we are very much confident that, okay, the power will be continuously coming. Why we are thinking so? Because you are using something like coal or petrol or diesel there outside to burn, and that is giving you the energy, and that production is continuously going on. A person is there who is dumping the coal continuously for us, such that this is happening. But when you consider this kind of solar energies and others, they will not be continuously there. Like if I just rely on without any storage, energy storage device separately, it is not continuous, okay? So if you consider solar or wind energies, they are completely dependent on time and weather, right? So if you consider sun, if I wanted like this AC, if I wanted to switch on, I cannot switch on the sun, right? Sun will be coming only for some time for us, right? And also it is highly weather dependent. Tomorrow it could be a monsoon coming and sun might not be showing up for several days. Then what we will do? We cannot simply rely on the solar energy. Same with the wind. And similarly, if you consider geothermal or hydro power energy sources, they are heavily again location dependent. Like if you wanted to use hot water or hot springs in order to generate the energy, they are like only at specific pockets of the whole world. Similarly, where you can construct a good hydropower project when there are some hills surrounding, so that you can have enough potential energy barrier in order to hold this whole water there, right? If that is not the case, then you cannot simply start a project like that, okay? And if it is very far from the place, then you have to think of how do you lay these lines and other stuff in order to get the power continuously. Again, these are all sources that are dependent on location, time, weather, etc., etc. So what is important for these kind of things is, wherever you are generating the energy, you need to store that energy, okay? That's the most important point. He already mentioned that. How do we store this? Okay, again, there are multiple kinds of mechanisms in which you can store. For example, you can just simply pump the water uphill and use it because you are increasing the potential energy of the water. You can use it again like to run the turbines or something. Or when you have the energy generated, immediately you can convert the water into steam. So steam is at a higher energy, so you will use it to again turn the turbines and again you can generate the electricity. Or you can use something called as flying wheel, okay, that will be rotating more, and you will increase the rotational speed of that one. That rotational energy will be later used in order to generate the electricity, and so on and so forth. So there are multiple ways to store the energy. The one that we are going to see today is just one of them, that is the rechargeable batteries that all of us are using already in our mobile phones or laptops or various other kinds of things. And here, what is the advantage? So you are able to not just use it once, but you are able to use these kind of batteries multiple times. That's the major advantage that we are achieving with this. And additionally, they are low cost and also portable. So as you know about your mobile device, you know that it is highly portable. Similarly, your laptop and any other thing. Why it is the case? Because you are storing the energy, and that is so lightweight that you can easily take it on your backpack and you can walk. So that's something that we need to see. And among the various kinds of rechargeable batteries, nickel, cadmium and so on and so forth are there. The only thing that is boomed up right now and majority of us are using is nothing but the lithium ion battery. So you can see the applications of this lithium ion battery all over the place right now. So including our electric cars or even the trucks and other stuff. And when you see the forklifts, auto bicycles and so on and so forth, obviously our computers, mobiles, all the things that we do know. Even if you consider a trimmer or a shaver, everything also has just this lithium ion battery, because it is very much having very high energy density that is required, and also it is very much portable. So what are the problems with, okay, let us first see what is the general description of this lithium ion battery. How many of you have seen this figure earlier already? Wow, cool. Okay, so what is this suggesting us? So here, this is the working principle during the charging as well as the discharging of the battery. During the charging, so this specifically will have two compartments, as all of you know, like any battery material will have at least an electrode, two electrodes, and as well as the electrolyte. Some of the batteries are there which they will have only one electrode, but we will not go into those details, like lithium air battery and so on and so forth. But here, this is the general setup where you can clearly see one is the anode, another one is the cathode. So typically the cathode is the one that is a host material, that is a normal material of the lithium. So like lithium cobalt oxide or something like that. So this is like a 3D material that will contain the lithium atoms by itself. Okay. And during the charging, what we are doing is we are actually you are applying the voltage and pushing these lithium atoms through the solution towards the anode. So what does this suggest? This is something that is high potential thing. That is, it is not a spontaneous process, rather a non-spontaneous process. That's the reason you are giving some energy to push the lithium atoms that are present in the cathode material to move towards the anode material through this particular separator. Okay, so here in between, whatever we are seeing, there will be some electrolyte like ethylene carbonate, propylene carbonate and so on and so. Okay, they are just solvent molecules essentially, through which this lithium ion will be traveling and it will be reaching towards the other end, where you have here the anode is graphite. You all might be knowing the structure. Here you can also see this honeycomb type structure, the stacked layers of graphene. These are nothing but the graphite. So here this red color dots corresponds to the place where this lithium atoms will be going and absorbing onto the surface. And once you disconnect, once you stop the charging, it will automatically start the discharge, right? This discharge is obviously a spontaneous process. Okay, as long as you have an external circuit that is connected, it will be automatically flowing, where the lithium atoms will be, donating the electrons to the graphene or the whatever the material, anode material is there, and it will be transferring back to this particular cathode, to the host material. Okay, this is the simple process which is happening inside our batteries on a regular basis. There are multiple things that will be affecting the stability of the battery or working of the battery or the storage and so on and so forth. However, basic principle is only this much. So what is the problem with the lithium ion batteries? Why are we trying to find other anode materials? As the topic of today's talk suggests, we are interested in finding new anode materials. What is the reason for finding new anode materials? Is the current lithium ion battery density they need for, like, right now you do know about the electric vehicles, majority of you might have seen. So why people are not still interested, or why people are scared to buy the electric vehicles immediately? What are the possible causes? Battery blasting is one thing that corresponds to the safety issue with the battery, but we are using also, some of the people will use gas cylinders. Gas cylinders also can blast, right? Even petrol car also can blast if properly blasted, but that's not the point we are trying to say. Okay, one aspect is definitely safety issue. Yes. Battery doesn't last that long. Okay, recharge points everywhere. But even when the recharge points are there, his point is very much valid, that we wanted, like, if you are considering like petrol or diesel, it hardly takes like maybe 5 minutes, 10 minutes for us to recharge fully. Recharge in the sense like you fill the tank fully. Whereas these are taking a lot of time to recharge. That means what is required? Something that can be quickly recharged is definitely necessary. Additionally, as he pointed out, our limit is very less. Like probably you can travel on a car for 200 kilometers or 300 kilometers with the current day batteries. But what we need is something like, I don't want it to recharge immediately. I wanted to go for like probably 1000 miles and then I wanted to start the recharge. That's what generally I would be expecting. So how do I get that? How do I proceed that? The only way for us is to improve the energy density. Like what we are saying is about energy which is required for to run the car quickly, right? That's all we are need. So how do we improve this energy density further? Energy density is actually defined as the voltage of the battery versus the specific capacity. Okay, specific capacity is how much amount of charge you can hold per gram. Okay, I have some material. This material, how much charge this material can hold? That's all it is, the first question. So that is given by the specific charge capacity, and voltage is nothing but, you guys have studied what is the voltage. It is telling you about the potential to perform the work essentially, right? So then when you are multiplying both of them, you have one side energy per gram, coulomb per gram, other one is voltage. Coulomb into voltage is nothing but EV, right? EV is nothing but, what is the unit of EV means? It's an energy unit, right? So that energy per gram is given by these two things. So essentially what we wanted to do, we need to improve the specific charge capacity. That means how much amount of charge a material can hold. If we can increase that one, that will automatically help us to travel long distances. And additionally, if you can get the cell voltage to be higher, that's another thing that we can benefit from. So cell voltage, we will see again how we define all of that. So essentially, we are interested in improving the energy density of the lithium ion batteries. So for that, what we need to find better cathodes, better anodes, better electrolyte materials, and everything better, whatever is possible to improve this one. But additional point that we should also see is, like when we told about, for example, the petrol or the diesel, the first slide that we have seen in the Russia-Ukraine war slide. What is the problem that we have seen there? It is highly affecting the world because the non-renewable resources here, the petrol and the diesel, are not equally distributed all over the globe. If India would have access to petrol and diesel a lot in our places, then we wouldn't be worried so much about, okay, what is happening in Russia and Ukraine, right? Similarly, when you are going to the lithium ion batteries, the raw materials that are used for the lithium ion batteries are not equally distributed all over the globe. That is a big point that we should be remembering. So this suggests that we should be trying to go, apart from the lithium ion batteries, alternative technologies that are equally available, at least whatever are available to India, right? So as you said, see here, whatever per kg, that's all it is. Like how much gravimetric is like weight wise, yeah, and volumetric is volume wise, that's all. How much the energy density can be there in a specific volume, because when you are seeing about your mobile phone, you want it to be less weight and also it to be as thin as possible. Both of those things is what they are trying to say. Because if the weight of the battery itself is adding, when you are, for example, running the car, that itself is a big thing, right? Like you need to minimize that one. Yeah. So what we are seeing here is the different problems that are associated with the lithium ion batteries, raw materials. What are some of the raw materials? For example, lithium itself is one of the raw material that you need. And as I said, the cathode material contains lithium cobalt oxide or various other lithium iron phosphates, many other things are there. But current battery contains lithium cobalt oxide. So which you need the cobalt a lot, okay? And where do you get the lithium resources? If you see, this is how it is actually there. If you see the first figure here, this figure corresponds to how do you get the lithium. How are we getting the salt in generally, like sodium chloride? How do we get that? Do you guys know? I mean, rough idea. So you will be first collecting the water and leaving it in the sun for some time so that it will be evaporating and finally lift. So the same kind of thing that you are seeing here, this is like a picture taken from the little bit above, okay, using a drone. And it requires, in order to extract lithium, it requires a lot of water. It's not that much easy and it's not coming from the ocean or something, okay. So this is a picture from the Argentina where they have actually very less resource of the freshwater resources. And they are actually using this whole freshwater resource, I mean majority, in order to just simply obtain this lithium, which is affecting obviously the environment, and it is not something that is a sustainable thing. Like I can drain out everything that is possible to me and the people there will immediately start dying, okay, and that's not what we want. Here you see the illegal mining progress like that is happening for the cobalt. Cobalt is majorly available in African countries, specifically Congo. So there what you would be doing, you are sending like kids just to extract some cobalt metal, whatever in the ore, okay. So this is again an inhuman practice that we are doing. So are we interested in doing that just for our benefit? Obviously no. So that's where again, as I said, the raw materials are creating huge geopolitical tensions. Again, for the case of lithium ion batteries, India only recently we found one place like in Kashmir and somewhere in Himachal Pradesh or Rajasthan also. So these are the places where we recently obtained the lithium ores, okay. But this is obviously will not be sufficient for us to rely on the lithium ion batteries. So accordingly, you will be trying to see the alternative technologies. Obviously, this is all going on right now, although sodium ion batteries has reached to some extent and some level they are already matured enough. So the alternative technologies could be sodium ion batteries, potassium ion batteries, calcium ion batteries, and so on and so forth. All of these things are possible and everything will have its own problem, okay. Like similar to the case of lithium ion battery, which has been developed for 25 years, we need to learn from the technology that we already got from the lithium ion batteries and we need to use that for developing the new batteries. And for each one of these sodium ion batteries, etc., you need to again optimize the anode material, you need to optimize the cathode material, and so on and so forth. For example, if you simply take the graphite that has been used as an anode material in the lithium, and if you put that simply replace that for the sodium ion battery, it won't work. When you put just the sodium, the specific charge capacity for the sodium ion batteries when you are using the graphite as the anode decreases heavily. That means it is basically useless. So what you need to use it, you need to find the new materials, and that's what we are going to see today. And only the thing that we are going to see in this talk is about finding the good anode materials, and again only using the computers. So what are some of the good characteristics of the anode material is what I have shown here. So these are the things that we will be calculating. So first one is the material should be stable thermodynamically, mechanically, dynamically, whatever it is, and act as a good electrical conductor. Obviously we are trying to see it as an electrode. This is an electrode material, so first of all it should be a good electrical conductor, and it should be dynamically stable, and also it should be thermally stable, because we do know that we wanted to use them for mobile phones, etc., where the safety issue would be definitely arising. So you need to keep them as safe as possible. That means thermally this particular material should not be degrading just by heating to some 40-50 degrees centigrade, right? That's the first point. Second thing is the material should have high affinity towards the metal ion. As we said in the beginning of the mechanism, what happens? You will be giving some voltage and the ions will be moving towards the anode and they will be sitting there. So in order for the anode to sit, in order for the ions to sit on the metal anode, what is required? The anode should be binding to this metal atom very strongly, okay? That's one of the first things that we would be seeing. And it should show a moderate value for specific capacity. As if it at least can give us like a better than what is existing, that would be useful. And why the strong binding is required is because if the metal ions are not binding strongly to this particular anode, it will slowly form the dendrite. They will start to agglomerate among themselves, like sodium clusters or a lithium cluster, like that it will happen, and these clusters will grow slowly and they will pierce the separator. Whatever the separator is there, that will pierce the separator and leading to the short circuit current, which can obviously create the safety issue and it will blow up the whole battery. Next one is anodic voltage. So as we said earlier, if you wanted to improve the energy density, what are the two factors that we told? Energy density, specific capacity, and voltage. And what is the voltage? Voltage of the cell we are meaning, and cell voltage is defined by the voltage of the cathode minus the voltage of the anode. So if I wanted the voltage of the cathode minus the anode to be very high, then the anode must be as small as possible and cathode must be as high as possible. That's another thing that we should be considering. So generally we should be trying to keep it between 0.1 or something like that. And next thing is the metal atom diffusion barrier on the surface of the material should be low. So one of you already pointed out that we need fast charging, like the materials should be able to do the fastly. How it will be possible? As you are seeing there, what happens? These ions will be coming and going to the anode material, and they have to, during the discharge, they all have to come back. And if you consider the conductivities, electron conductivity will be very high when compared to the ion conductivity. Are you guys with me still? Electrical conductivity will be much faster because electron is a very small particle that is going through there, okay? If you are seeing that as a particle, not as a wave, okay? So that's something that will be going very quickly. The electrical conductivity in copper wires, etc., are much higher when compared to the ion conductivities. And ion conductivities themselves are very high inside the solution when compared to the solid, okay? So what is the rate limiting step if you are thinking of here is definitely the ion conductivity in the solids. What are the solids that we are using here for the ion conductivity? So this is nothing but your cathode material and the anode material. If somehow we can do this ion conductivity in the cathode, in the anode quickly, that if that becomes more, then we are solving the problem. That means we need to, here in this case, particular case, since we are concentrating only on the anode material, if the ionic conductivity of the material is better, then obviously we are helping the battery there. Finally, after metal atom insertion, interlayer expansion of the anode should be low enough so that it can retain its original structure. You don't want your mobile phones to bulge whenever you are charging, and when you are discharging, they should not be shrinking, right? So you wanted the material to be as perfect as possible. So this is additional thing that we would be seeing. So what are the major points that we will be checking? First one is about the stability of the material, thermodynamic stability, etc. Second thing is about the conductivity, electrical conductivity, whether it is a metal or not, we would be checking. Third one is whether it will be able to absorb the particular metal atom strongly or not. That's what we will be dealing with. Next, once you have the anodic voltage, we will try to see if any material is having very low energy, a low voltage or not, average voltage. And then the metal atom diffusion barrier should be as low as possible. Metal atom diffusion barrier is nothing but how quickly you are removing and how quickly you are able to put on the anode surface. And finally, whether this material is able to bulge or it is stable or not. These are the things that we will be seeing. So how do we choose the materials? There are like hundreds and thousands of materials that are available there, okay? In this specific case, what we have chosen is like a recent material called antimexenes. So these are nothing but transition metal nitrides or carbides, okay? Transition metals, all of you know, carbon you know, and nitrogen you know. So these are the materials that corresponds to, for example, this is the aluminum and titanium carbide. So these are also called as max phases. And if you just remove this, make this as layered materials, like here the carbon and nitrogen are coming, or carbon and oxygen are coming here. So these are called as mexenes. These are like layered materials. So you can see that stacks are there. If you are here, so these stacked materials are called as mexenes. The reverse of them are what are called as the antimexenes, okay? So here the metal atom will be there at the center, and the non-metal ion like sulfur, selenium, etc., they will be there above and below. So these are called as antimexene materials. These are recently discovered in 2021. So we tried to see these materials whether any of them will be useful as anode materials or not. That's our major interest. So these people, Gu et al. Have discovered about like 27 or so anode materials here. So of them, we have just considered 6 of them. All of them corresponds to the cobalt containing systems. There is no specific reason for choosing them, only just that these are the few materials that have the cobalt and other non-metals. I could have chosen, for example, rhodium or rubidium or anything, that doesn't matter, okay? So we just choose these 6 materials to see whether these are actually useful or not, okay? So this is how the optimized structures would look like. So in general, in computational chemistry, what you would be doing is, first you need to prepare the cell, okay, whatever you have. So these materials, whatever you are seeing, as I said earlier, these are 2D sheets, 2D materials. How do you generate the, first of all, coordinates for these 2D sheets, okay? One simple way would be, if you know the bond length between the atoms, you can draw your own structure and give the x, y and z coordinates of this particular systems into the computer, and then you would be doing the optimization of this particular structure. What is meant by optimization? Optimization means finding the minimum positions of this particular atoms, okay? So if you draw some structure, you could have kept carbon here, another carbon, like if I ask you to draw benzene on a paper, you can draw any way you wanted, okay? although the proper way will be 1, but you could have drawn any way. But that will be not the optimized structure, right? So you need to then put the geometric constraints in order to completely first optimize this structure. So these are the optimized structures, and this is like the top view, and this is like the side view of this particular systems. As I said, we considered cobalt, arsenide, boride, phosphide, sulfide, selenide and silicide. And these blue color atoms are the ones that corresponds to the cobalt in all the systems. I will be showing some of the figures on phosphorus and sulfur, but similar kind of results were also obtained for other systems that I will not be discussing. So this here corresponds to what is known as the
in computer, you have some mathematical modeling for it, right?
correct.
So I already have some idea of what mathematical modeling of it might be. Then what am I actually doing?
Okay, so mathematical model is giving you here, in this case what we are doing is what is known as the density functional theory. Okay, so this is a theory that is useful for anything. Like if you heard of quantum mechanics can be used to study any system. Okay, whether you are able to solve it analytically or not is something that is different. For example, if you consider a hydrogen atom, you will be able to solve the system completely using the analytical tools. Whereas if I go to just simply helium atom, quantum mechanics does not give me any analytical solution. What is meant by analytical solution? Any other answers? What is an analytical solution? Numerical values. Analytical solution is something like, for example, for the case of particle in a 1D box, you have energy. If I want, I can simply write as a formula. Sorry? Yeah, mathematical only, but it's something like a formula that you can write and you can easily obtain the value by just substituting the values there. However, for once you go to the helium or something, you cannot obtain such kind of analytical derivations. Okay. Now, when we go, what kind of mathematical model you said? So all of us are solving the same thing, that is time independent Schrodinger equation. Time independent Schrodinger equation is something nothing but H psi is equals to E psi. Have you heard of this matrices? This particular one you had? Very good. So that's all we are essentially solving. H psi is equals to E psi is the problem that you are solving. So every detail of this particular material will be going inside the computer through that Hamiltonian H. That's all. Okay. So it is not that mathematical model is there. What you are solving means the mathematical model is there just as a Hamiltonian. That's all. How do you write this Hamiltonian and how do you solve this entirely corresponds to this optimization problem. Okay. The general procedure includes like you write the Hamiltonian and you diagonalize that Hamiltonian in order to obtain what are called as the eigenvectors. Once you have the eigenvectors, you can use them in order to construct the wave function. Wave function is nothing but your linear combination of these eigenvectors. So once you do that, you will have the wave function. So you can use the Hamiltonian operator in order to get the ground state energy. And similarly, when you are doing the optimization, what you will be having is, as I said, like you might be starting with some stupid structure. You wanted to actually get to the proper structure. How do you do that? You will be optimizing, minimizing. So there will be various kinds of algorithms that are available in order to minimize. Like simple ones could be gradient descendant, Newton-Raphson method, and so on and so forth. Have you heard of Newton-Raphson method or something? Yeah. So such kind of methods you would be using in order to find the local minimum. That's what is called as the geometrically optimized structure. So here geometrically optimized structure corresponds to these ones. So once you have that, then you can start calculating various properties. So here we have calculated what is called as the phonon spectra, and according to this phonon spectra, we can identify whether it is dynamically stable or not. In this case specifically, without going into the details there, if you have any negative values that suggest that this system is not stable and your atoms needs to be changed along that particular direction. In this case, as you can clearly see, all of them have only positive values and positive dispersion, simply suggesting that these systems are stable. So since these are dynamically stable, you can start working with these materials. So these are some of the what are known as the electron localization function plots. From this you can clearly see, for example, these are, as I said, blue color atoms corresponds to the cobalt atoms. See here. So here, as I said, the blue color atoms corresponds to the cobalt atoms, that is the metal atom, and the other things are the non-metal atoms. You can clearly see that the electron density is majorly localized on the non-metal atoms. What does that suggest? That means electrons are only majorly there. That is like this is an ionic type of interaction that is happening between the anion and the cation. Here it is the non-metal and the metal atom, and that is what is stabilizing these systems. We already saw that these systems are stable through the phonon spectra, but how it is stabilized, what is the reason for the stability? Here it is the ionic type interaction, not the covalent type interaction. Next, we calculated whether these systems are metallic or not. Last time when I came here, you guys said that some of you only know about conduction band. Now the things have changed. Were you taught about conduction band, valence band, etc.? How many of you do not know conduction band? Okay, then it's good. We will learn something about it. So this is what is called as something like band structure. Okay, you have to listen now. So what is the band structure? How are we getting? Okay, you do not need to worry about those lines that are there. So in general, if you consider a molecule, okay, you have seen probably ethylene or something. Have you heard of Huckel molecular orbital theory or something? At least molecular orbital theory? Yes. So there what you have atoms, you bring them together and you write those energy levels, and then in the center you will be writing the molecular orbitals and their energies. So these are like the energy levels, right, that you have. So this is for one particular molecule or two atoms that you are writing. When you are considering a solid, how many number of atoms will be there? A lot of atoms will be there. So each of these atoms will have their own energy levels, and you are trying to bring all the atoms together to one place. Okay, so that means you can imagine that one atom will have the starting level here, another atom might be slightly here, only slightly different, third atom might be slightly lower, and so on and so forth. Like this, when you have millions and millions of atoms, these levels that you are seeing will form something like a band. And that's what we are calling as the band theory. So here whatever you are seeing as a band, for example in the bottom, this is comprising of many energy levels at each and every k point here. We will not worry too much about it, but these are the bands that are there. And similar to the case of molecular orbital theory, where you are actually filling one after the other, right? When you get the molecular orbital theory, the center place, you will be first filling 2 electrons in the 1s orbital, next 2 electrons probably in the 2s orbital, and so on and so forth, right? The same way you will be doing here for each of these bands. This band corresponds to the electrons, so this band corresponds to these energy levels only, and you will be filling them. And the end point where all your electrons are over, that's what is often termed as the Fermi level. That's the level at which you will not be, above which we will not be actually putting the electrons. Okay, and below that whatever the band is there, that band is what is called as the valence band maximum. Okay, that means the valence electrons can stay there, and that's the band that is the maximum where you can fill in. Above which whatever is there is called as the conduction band. The lowest one is called as the conduction band minimum. Okay, so here if you see, this is what is the dashed line here, horizontal dashed line. This is what is called as the Fermi level. Okay, we have scaled the Fermi level energy, that's why you are seeing 0 here. In general, Fermi level energy doesn't need to be 0. We just considered if Fermi energy is 3, every energy level we have kept x minus 3. That's what we have done here. Okay, that's the reason it is showing at 0. So these bands are the ones that you are trying to fill one by one. And this band, whatever you are seeing here, for example, this band is the valence band maximum, and this band corresponds to the conduction band minimum. Okay, important point about that is important for us is, if there is a metal, then the conduction band and the valence band will be passing through the Fermi level. That means if you have finite number of bands that are crossing the Fermi level, that's what you call it as a metal. Whereas if it is a semiconductor, there will be a small gap between the conduction band minimum and the valence band maximum. And if it is an insulator, this gap will be huge. Okay, these are the differences. You guys are able to follow what I am speaking here? So you have simply conduction band, valence band. If there is a gap between them, that's called as a semiconductor. If the gap is very high, that is called as an insulator. Okay, if for a metal, the bands will be crossing with each, crossing the Fermi level. You can clearly see, for example, here cobalt arsenide is there. What you are seeing at the Fermi level, the bands are crossing the Fermi level, right? Similarly here, if you see, one of the band here slightly is crossing. Here you can see again they are crossing, and so on and so forth. All of these cases the bands are crossing, suggesting that these materials are metals, insulators, Semiconductors, which one? Metals, right? Additionally, like we have also plotted what is called as the projected density of states on the right hand side. What we are essentially doing is, like, once you have this big crystal system, what you are doing is you wanted to know which atom is actually contributing to this specific band that we are seeing. So when you do the molecular orbital theory, what you will be doing, you know the atomic orbitals that you are putting, okay, you will say n pi star, pi star orbitals are coming, whatever the kind of bonding that you have. But here, how do I know which band is coming from where? For that, I will be trying to see what is known as the projected density of states, okay. So this one will give me the idea of which atoms are actually contributing to the which specific band. Here on the right hand side, you can see, so here the CO PDOS is shown in the red color, COX DOS is shown on the blue color, and only the X atom, X corresponds to here arsenic or sulfur or something, that is given in the red color. So let us consider any one of them, the center one. So here if you see, the orange color and the blue color are merging with each other all over the place. That suggests that cobalt atoms are majorly contributing to this particular portion which we are seeing. There are also minor portions that are coming, but majority is coming because of the cobalt. And specifically, even if you see closer to the Fermi level, all this place, that is essentially, we have done additional plots also, that is coming because of the d orbitals of the cobalt. Why this kind of information is important? When I, for example, shine light on this system, okay, so electrons will be going from the valence band maximum to conduction band minimum. That's the easiest excitation because the energy difference between them is very little. So when I shine the light, the electrons that are there in the top, they will be just simply going up. So what does this information tells us? These electrons are going to go from the cobalt to something else. Cobalt d orbitals are the places from which the electrons will be removed, is what this information is telling me, okay. So as such, what we are learning from this particular one, first of all these materials are good, they are metals, so that means they can be used as the electrodes. And one more thing that we are learning is, it is the cobalt that is giving this metallicity of this particular material, okay. Next, as we said, we need to understand whether they will be binding strongly or not, okay. To find out whether they are binding strongly or not, I need to calculate what is known as the adsorption energy. So the conductivity, it is related, but the conductivity is often more described based on the curvature of these bands, okay. So if you have something like a flat band, that suggests that it is, so how this is coming is, again, if you know the momentum is given as h bar k. Do you guys know this? At least you might have known about de Broglie relation, right? P is equals to h by lambda, that much you know. So that means if the curvature is going like that, equals to P is equals to h bar k, and kinetic energy of the electrons corresponds, if you are writing that as h cut square k square by 2m, p square by 2m is the kinetic energy. Since P is equals to h bar k, p square by 2m is h cut square k square by 2m. So now what we have plotted here is corresponding to energy versus k points, okay. So in this E versus k relation, what we are plotting essentially is E versus k. So if this is having a high curvature, so essentially kinetic energy corresponds to, as I said, roughly this is all h cut square k square by 2m, okay. So if the curvature of this d square E by dk square, that's what you would be actually calculating to know the curvature. If that curvature is more, that is suggesting you that the electron's conductivity will be much better, okay. That is highly dispersed band, that's what it suggests. If the curvature is more, that means it is a highly dispersed band, and a highly dispersed band means the electrons are delocalized all over the place. Conductivity will be more, whereas if it is a flat band, there is zero curvature, that means it is a localized entity, that means the electron will be there on either cobalt atom or somewhere, that means that cannot be useful much for the conductivity. So as I said, like we need to find out the adsorption energy right now. So why we are trying to calculate the adsorption energy? This is to again see whether the system, these atoms after adsorbing, whether they will be agglomerating or whether they will be able to go on to a site and stick there and come back. That's what is our aim, okay. So obviously this is our unit cell. So like when I say about the graphene or any other anode material, there is a big sheet that is there, but I don't want it to study the whole sheet because this is essentially a crystal type, like it is symmetric periodic system. So if I consider simply the unit cell and study its properties, the properties will be the same across the all over the other place. So I consider this unit cell and I need to find out now what are the possible sites there it can be absorbing. So accordingly we will be calculating. So in this particular case, these are the asymmetric unit that you can see here. I can actually do the reflection along this line to obtain this direction and use that to completely consider the full cell. So in this asymmetric cell, there are about 6 sites that you can see. For each of these sites, I will be calculating the adsorption energy and I need to find out whether which one is the most stable site. So why we are considering the most stable site? Because if the adsorption energy is most stable there, then obviously when I am just sending these ions through the electrolyte to the anode, those are the places that will be going and sitting first, right? If you assume that I am just sprinkling these ions on this anode material, so where these ions will go and sit? Wherever they can bind strongly. Those bindings are what we are calculated here. And here you can see for each material we have calculated the lithium ion adsorption, sodium ion adsorption and potassium ion adsorption. So for each of these things what we observed is this S3 site, this is the site which corresponds to the S3 site. This site is more stable when compared to S1 and S2, okay. These are just names, there is nothing to remember here. We found that this particular site is the most stable site. And among these 3, potassium is the one that is adsorbing to these systems strongly. Potassium greater than sodium, greater than lithium. So this is what we have computed here. S3 is not same as the S2 because S3 is actually down. I mean, you cannot, if you remember this particular picture, so you can see that this is S3 site actually. I mean, on top of this one we will be considering, this is the S2 site. Yes, so that you will be seeing. So S3 is not actually 4 connected. S3 is having, this is the position of the S3 and we will be keeping the atom somewhere here because we will not be going down inside that one. We will be keeping it away, okay. So the S2s will be there. So as I said, these are 2D materials. So this is all we have here. This is not a 3-dimensional structure. So what we will be doing is we will be stacking them like one after the other. In between them there will be a vacuum. And that's the place where you wanted to actually send these sodium or lithium ions and keep them adsorbed. So what we obtained is S3 is always greater than S1 greater than S2 and you can clearly see here the values also. Immediately you can notice that. And similarly potassium adsorption, for example on the cobalt arsenide is like about 1.7 whereas on the sodium it is minus 1.2 and the S3 it is minus 1.3. So that immediately suggests that generally this is the trend that you are going to get, potassium greater than sodium greater than lithium. This is the new thing that we obtained. How do you calculate generally these adsorption energies? You simply calculate the energy of the composite. What is the composite? Both the metal atom and the anode you calculate and simply calculate the energy of the anode, and so you just subtract this one and also energy of the lithium atom or the sodium atom or the potassium atom. How do you obtain these energies of each of the system? Use your HI is equals to E psi. So this E is what corresponding to the composite or something and then you calculate. Although I have written simply HI is equals to E psi, the calculation procedure involves a lot and essentially what we would be using is what is called as the density functional theory. We are not going into those details here. So essentially we obtained that these energies are, as you could see, minus 1.3 electron volt or something, which are more like a strong physisorption or close to chemisorption rather than actually the opposite, okay. These are not very less values, these are in electron volts. So this suggests automatically that all of these atoms will be strongly binding to the material and that's a good sign for us because that suggests that they might not be forming any dendrite. So here, in order to understand why the S3 site is more stable, what we have plotted is charge density differences. Similar to the case here, whatever we have shown about the energy, so you can also calculate actually the total density. As I said earlier, we are doing the density functional theory, but even if you are not doing, what is density? If you know wave function is psi square gives you the probability density, right? That's what it is. Have you guys heard this or no? Yes. So this is probability density which is related to that rho. So this is what we are going to plot of the entire system. So if you consider the composite system, and same way like this, if you subtract for the anode and subtract for the metal, what you would be seeing is the difference between them, okay? That difference is plotted here, where charge accumulation is shown in this cyan color and charge depletion is shown in the magenta color. So accordingly, you can see that from where the charge is depleted for each of the system, you can see that the metal atom is the one where the charge depletion, this is like the adsorbed metal atom, charge depletion is happening there and the charge is accumulated on the non-metal atoms, okay? So for each case that is the same, and here we have shown only for the cobalt phosphide, for the lithium, for the sodium and for the potassium. And you can clearly see that lithium is donating the electrons and it is going to 4 particular atoms there, okay, 4 non-metal atoms. Whereas for the case of S1 site, it is only going to 2 atoms. And for the last one, it is going to only 1 atom. This is happening because of the site also. What does that suggest? The S3 position, when you are actually donating the lithium, and when the lithium atom is donating its electrons at the S3 position, it is able to donate it to 4 atoms and it is able to bind with 4 atoms. When you are able to bind with 4 atoms, your anchoring position will be very strong. That's why it is able to bind strongly. The other hand, S1 is only binding to 2 atoms, so that is somewhat a weaker one, and S2 is even weaker because it is having only 1 atom with which it is binding. So that's the understanding for why S3 site is greater than S1, greater than S2. Similarly, if you see, like, we can get some understanding of the charge densities, etc., based on which we can further say that, okay, potassium is able to adsorb strongly when compared to the other systems. Additionally, you will also have a lower distance when you actually calculate. I did not show those results here. If you calculate the distances also, there will be slight differences in this particular case. So once we understood 2 things, one is whether this adsorption is very strong or not and what is the reason for the adsorption. Then we went on to see whether the migration energy barriers, whether they will be low or high, okay? So accordingly, again, when you are considering this material, I need to compute various paths that this particular metal atom can go through. It's not like only one path it will be going through. So accordingly, we have calculated path 1, path 2 and path 3. These are the 3 paths through which this metal atom would be going, and we find that path 1 is the one that is the having least barrier, okay, among this path 1, path 2 and path 3. So I will show you why that is the case. So if you see from S3 to S3, so the simplest way according to the CDD plots that I have shown, the charge density plots, if you remember, at the S3 site, there are 4 of these bonds that are there formed, whereas for the S1 only 2 of them are there. S2 will be having only 1 site. So when it is moving from S3 to S1 to S5, what is happening? It is having 4 bonds, it is breaking 2 of the bonds and forming another 2 bonds, whereas at the end it is again gaining the 4 bonds. Whereas when it is going through this particular path, it will be breaking 3 bonds and forming only 1 bond and coming back to again 4 bonds. So when you need to change this one, you can immediately see that S4 to S2, S4 to S1 is the one that is actually having less changes when compared to the original site. That's one way to understand the lower barrier for the path 1. Is this clear? Okay. So, and additionally what we are seeing is lithium, sodium, potassium. Potassium is the one that is having the least barrier. You can see here red color corresponds to the sodium, blue color lithium, and potassium is the one which is having the least barrier. This is for path 3 and this is for the path 1. So obvious question is why potassium is having the least barrier, okay? And one more way, if you see, this is actually counterintuitive. If you remember the earlier adsorption energy values, potassium is actually having the highest adsorption energy. If potassium is adsorbing strongly, what would you expect for its migration energy barrier? Potassium is the one that is adsorbing strongly. Now I wanted to move this potassium atom from one site, one stable site, to another stable site. Here the stable site is S3 site. What I am trying to do? I am trying to move from one S3 site to another S3 site. So potassium is the one that is adsorbed strongly. So what would you think, like what should be happening? Which one should have the highest barrier according to these adsorption energies? Potassium should have highest or least? Highest. Why we are thinking that way? It will be very difficult to break the bonds. The counterintuitive point here is we are actually not completely removing the potassium atom from the entire surface, and again we are not putting it. What we are actually doing? We are just moving from one place to the other. Now you think again, if I need to move from one small hill to another small hill, okay, all I need to worry is about the difference between the heights of these two hills. Whereas here, what does the difference between the things that I need to consider? Difference between the, earlier you thought something about on what basis you said that potassium should have the highest barrier? Adsorption energies. Now what it should be? Should it be simply the adsorption energies? It is the differences in the adsorption energies across the sites. That's what you should be looking at, not simply the adsorption energy. If the difference between this site and this site is less, then the amount of energy that is required for it to migrate will be minimum. Whereas if that is very high, then the migration energy barrier will be more. So now let us go back to these adsorption energies simply, and let's take for the case of potassium, okay. I am showing you for the case of phosphorus, so let's look at this particular line. So what is the adsorption energy difference between S3 and S1 here? Roughly 0.3, right? And how about this one? If it is going through S2, S3 and S2 is about 0.6. So one is 0.3 and another one is 0.6 for cobalt phosphorus. So let's see that one. So for the potassium, one of the barrier is roughly how much? 0.3. Another barrier, potassium, this is that one, roughly 0.6. You are able to see that, right? The adsorption energy differences are roughly matching that of the these barriers. These barriers are calculated actually using another technique called climbing image nudged elastic band. But the understanding for us is it's roughly the energy differences that between the sites. This other one, when you are considering, let us consider the lithium atom. For the lithium, how these sites are there, let us see. Always remember that when I am going along the path 1, I am going from S3 to S1, whereas for this one it is S3 to S2 to S3. That's how I am going. So if I go back to, let us consider simple one is sodium. Let us see the sodium for the cobalt phosphorus. The difference between these is again roughly about 0.4. This is 1.7, this is 1.3, and between this one is about 0.8. So let's go ahead and see the differences. One is 0.4, so that is roughly here, okay, red line. Another one is roughly 0.8, you can see here, okay. That's what we are doing. So essentially what it is telling you, when you are trying to do this migration, when you are calculating the migration energy barriers, what will be the one that will be affecting? It is the adsorption energy differences, not the simple adsorption energy. If we were thinking about simply the adsorption energy, then what you would have thought? Potassium would be the one that will be having the highest barrier. But when you see the adsorption energy differences, you can immediately see that it is the potassium that will be having the least energy barrier, okay. We can further understand this by like just plotting all the sites that are in between S3 to S1. So here when I am drawing, I did not calculate and show you the difference in energy between the S5 and S3 also, right. So that's also something that we need to consider. I just considered S3, S1 and S3. That's all I did. So we can do that. We can calculate the diffusion energy barriers for each one of them. So these are shown again separately for all the other materials also, okay. So when you calculate, so this particular concept that I told you just now, like using the adsorption energy differences can be used to calculate the diffusion energy barrier not only for a specific metal, but also across the metals and also across the surfaces. These all can be studied. So here if you see three of them, obvious thing that you are seeing is potassium energy diffusion barrier is low. But among all of these things, this particular one, this corresponds to the cobalt boride. That's the one that is having the least migration energy barrier. This again can be obtained by just going back to this cobalt boride and check for the energy differences here. So if you compare cobalt boride and cobalt phosphide, which we have done, so this is like you can see 2.17 and 1.98. How much is the difference between these two? This is 0.1 to 0.2, that's the maximum. Whereas here it is about 0.3. That's the reason you are seeing that cobalt boride will be having the least barrier. Okay. So it's not only helpful for you to understand whether a particular element, that is a potassium or a sodium or lithium, is faster or not, but across the materials also you would be able to easily identify which one is having the least migration energy barrier. Okay. No, yeah. So that's how you will be doing, and obviously low diffusion energy barrier means faster charging rate. You can quickly remove that atom from one place to the other. And as I said, like we can calculate intermediate sites also, and you can calculate the adsorption. And as I said earlier, it was like slightly mismatching. So that slight mismatch also can be removed if you calculate for all the sites, and if you can see exactly the value will be matching for you. And that's what we have shown here. And this is how it will be going from one side to another side. I think one of you asked what is the S3 side. So this is how the S3 side would be looking like. It is a little bit down. From there you are actually crossing through this cobalt atom to again another S3 side. That's the reason you are seeing this minimal energy barrier.